Welcome to the Power Electronics class. Myself B. Veernarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. So we are in second unit, AC to DC converters. So in the last class we complete the three-phase half-wave converters with R load. Here so this is circuit representation of three-phase half-wave control converter with R load. Already we complete in the last class. That is the circuit diagram. Here is the output voltage waveforms for different firing angles. If you go through this three-phase half-wave converter for alpha less than 30 degrees with resistive load, it should be operates in continuous conduction mode, and alpha greater than 30 degrees we are able to operate in discontinuous conduction mode. Here these are the representation of three different firing. For corresponding the three different firing angles, the output voltage waveform should be represented like this. Here this is for alpha equal to 0 degrees, and here it is for alpha equal to 30, and it is alpha equal to 60. If you go through the alpha equal to 60 degrees, here we have the discontinuous conduction mode, and here it is the average DC output voltage 3 root 3 Vmp by 2 pi cos alpha, and this is the output voltage waveform for alpha greater than 30 degrees 3 Vmp by 2 pi 1 plus cos 30 plus alpha. So coming to this today's class, we are going to explain the three-phase half-wave converter with RL load, and later we will go through the three-phase full-wave converters. So if you go through the three-phase half wave control converter with RL load, here this is a circuit diagram. It consisting one isolation transformer whose primary winding is connected in delta fashion and secondary winding is connected in the star fashion. In each phase we keep a single SCR and the load is connected between neutral point of the secondary winding of the three-phase transformer to the common cathodes of the thyristors. Here we have three thyristors which are numbered as T1, T2, T3, and the combination of resistor and the inductor is connected as the load. Out of these three SCRs, we know the phase which is more positive corresponding the thyristor comes to the forward biasing mode. If you provide the gate pulse to the forwarded SCR, then it comes to the forward conduction state or on state. So we already discussed and we draw the output voltage waveforms in the last class for alpha equal to 0, 30 like that. Here I just want to draw the output voltage waveforms for alpha equal to 15 degrees and alpha equals to 60 degrees. For these two cases I just want to draw the output voltage waveform. Before goes to that, we draw the timing diagrams. For example, if you choose alpha equal to 15 degrees, then what is the conduction of T1? T1 conducts from, you add 30 degrees by the default. Why? Because from 30 to 150 onwards only T1 comes to the forward bias. So T1 conducts from 45 to 165 degrees and T2 conducts from 165 to 285. T3 conducts from 285 to 405 and similarly 0 to 45. If you choose alpha equal to 60 degrees now, so here T1 conducts from 90 to, why? Because 60 plus 30, 90 to 210 actually, but up to 180 only we have the positive portion. Next, T2 conducts from 210 to 300 and T3 conducts from 330 to 420 degrees. We will see the output voltage waveforms. So if you choose alpha equal to 50, 0 to 45, T3 conducts. So if T3 conducts 0 to 45, na, you mark that one, 0 to 45. This one is the 45 and it is 165, 285, this one is the 405. So 0 to 45, T3 conducts. If T3 conducts, output voltage simply follows Vc naught. So where is the Vc naught? Here it is, 0 to 45 degrees up to this instant. So this portion is available across the load like this. 45 to 165, T1 is in the on state. If T1 is in the on state, output voltage follows Va naught. So where is the Va naught? This one, 45 to 165 up to this. So what you are getting here? Like this. And 165 to 285, T2 is in the on state. If T2 is in the on state, simply you follow Vb naught. So what you are getting output voltage? Like this. After this, again Vc naught. So here it is the T3 will be in the on state. Here it is T1. It is T2. Again here T3. So you can observe here If you go through this RL load or R load, the output voltage never reaches the zero. Hence why you continuously have some current in the load side. So that is simply said to be continuous conduction mode. And here you have RL load now, depends upon the value of inductor. We know the converter may be operates either in continuous conduction mode or discontinuous conduction mode. If you keep low value of the inductor, then we are getting the discontinuous conduction mode. If we keep high value of the inductor, continuous conduction mode. First we go through the continuous conduction mode. Assume high value of the inductor. So here the conduction of each SCR is 120 degrees. So if you trigger the T1 at 60, it comes to the on state at omega t is equals to 90. 90 to 210 degrees it will be in the on state, and 210 to 330 it will be in the on state. 330 to 450 it is in the on state. So I am going with the continuous conduction mode, and here alpha equal to 60, that means 0 to 90, first 90, 210, 330, next 450. So if you go through the continuous conduction mode, then the output voltage waveform is, see, 0 to 90. What happens? 0 to 90, T3 will be in the on state. If T3 is in the on state, the output voltage waveform simply follows the VC naught. So 0 to 90 na, this one, 0 to 90, this portion. So what you are getting here, this is 60 na, so this one, and 90 to 210, T1 will be in the on state. If you go through the timing diagram, you easily understood. 90 to 210, T1 is in the on state. If T1 is in the on state, output voltage simply follows VA naught. So what you are getting here, 90 to 180 and 210. So here 90 like this, and 210 to 330, T2, next T3. So here this is the conduction of T1, sorry, this is T3, it is the T1, and it is the conduction of T2, next T3. So here actually from 0 to 180, VC naught is positive. See, VC naught is positive. Sorry, 0 to see 0 to 60, VC naught is positive. So here this one, VC naught is positive, and 60 to 90. You have the negative pulse, but due to the presence of the inductor, from 0 to 60 there was some energy must be stored in the inductor. After 60 degrees, even though the output voltage is 0, the output current cannot be 0. So the output current should be available due to the discharging condition of the inductor. So the energy stores in the inductor here, actually from 0 to 60, due to the conduction of T3, here this is the current flow through the circuit, this one. So in that condition, there was some energy must be stored in the inductor. After that 60 degrees, even though the negative voltage is available across the T3, the energy stored in the inductor is caused to maintain the on state of T3 continuously, even though the negative half cycle will be available across the T3. Why? Because see, the energy stored in the inductor is discharged through the load through the same thyristor. Hence why the T3 will be continuously in the on state. So you are getting up to the next instant, that is at 90. T1 is the incoming SCR. Up to that, this T3 maintains its on state. So at omega T is equal to 90, T3 goes to the off state and T1 comes to the on state. Similarly here also, from 90 to 180, the energy stores in the inductor during the positive half cycle of the supply. After 180, the energy stores in the inductor is discharged to the source through the thyristor T1. Hence why we are getting the negative pulse. We already said in the output voltage waveform we have the positive portion, that is the representation of some energy is transmitted from source to the load. If you have the negative portion of the output voltage now, that is the representation of some power should be transmitted from load to the source. So if you have the continuous output voltage like this, the negative pulse is continuously available up to the next instant, where the next incoming SCR is comes to the on state. If you have the negative pulses like this, then we will easily say it is the continuous conduction mode. It is the continuous conduction mode. If you go through this output voltage expression for this continuous conduction mode, this is the same derivation. Here it is. This one. 30 plus alpha to 150 plus alpha. If you go with the continuous conduction mode with RL load, the average DC output voltage expression should be same, like 3 root 3 Vm P by 2 pi cos alpha. We are getting the same expression. Why? Because if you choose alpha equal to 60 now, where T1 conducts 90 to 210. So see here, 30 plus 60, 90, 150 plus 60, 210. Limitations are fulfilled. For completion of one full cycle, we are getting 3 pulses in the output voltage waveform. So 3 by 2 pi integral 30 plus alpha to 150 plus alpha Vmp sin omega t d omega t. So by simplifying this expression, we already done. Finally, you are getting V0 is equals to 3 root 3 Vmp by 2 pi cos alpha. Here this is the operation and output voltage waveforms for continuous conduction mode. If you go through the discontinuous conduction mode, what happens? Discontinuous means we have low value of the inductor. So 0 to 60, some small amount of the energy must be stored in the inductor. Okay. Between 60 to 90, the energy stored in the inductor is completely discharges and the thyristor may goes to the off state. So if the energy stored in the inductor is discharges before the next incoming SCR, then we have discontinuous conduction mode. So if we go through the discontinuous conduction mode with RL load, how that output voltage waveform should be changed? Observe here. Yes, for alpha equal to 60 degrees, I just want to draw the discontinuous conduction mode waveform. So observe here, 0 to 60, no problem, T3 will be in the on state, hence why we have the positive portion. So 0 to 60, no problem. Due to this, there was some energy must be stored in the inductor, and assume that extension angle is taken as 15 degrees. That means after the positive half cycle, assume 15 degrees the SCR will be maintained on state due to the conduction of thyristor. So from the 60 to 75, you have the negative portion in the output voltage waveform. This negative portion will be occurs due to the discharging condition of the inductor. Hence why the energy stored in the inductor is transmitted to the source through the thyristor. And here in this instant, all the SCRs will be in the off state, hence why output voltage is 0. And again here this one and this is 0. Similarly here also and this one Next, here this is the conduction of T3, it is the conduction of T1, and it is the conduction of T2. Next, T3. You can observe in the previous class we discussed continuous conduction mode. That means in the next incoming SCR at omega t is equal to 90, T1 is the incoming SCR, T3 is the outgoing SCR. The current is immediately transmits from outgoing SCRs to the incoming SCR, hence why we have continuous conduction mode. Before the incoming SCR, if SCR is going to the off state, then see here in this portion the output voltage is 0. Similarly here also and here also, and if you go through the current waveform also, in this portion the current is 0. Hence why this is the representation of discontinuous conduction mode. That is the representation of discontinuous conduction mode. Here this is the simple output voltage waveform, and if you here no need to derive the output voltage waveform, mostly we have continuous conduction mode. Just you understand how the output voltage waveform should be changes under discontinuous conduction mode, that is enough. Clear? This is a simple representation of three-phase half wave controlled converter with RL load in discontinuous conduction mode. Next, we go with the three-phase full wave converters. So here the three-phase full wave converters are used to improve the output voltage waveform, and if you go through the three-phase full wave converters, we are able to collect the 6 pulses in the output voltage, whereas in three-phase half wave converter we are having only 3 pulses for completion of one full cycle. If you go through the three-phase full wave converters, we are able to collect the better output voltage waveform and better performance over these three-phase half wave converters. So if we go through these three-phase full wave converters, so first we go through the circuit diagram. In this three-phase full wave converter also we have midpoint type configuration and the bridge configuration. In our curriculum we have bridge configuration, so simply we go with the three-phase full wave bridge type converters. So here it is a three-phase fully controlled converter, sometimes it's called, or three-phase full wave converter with RL. Coming to the circuit diagram, Here if you want to draw the line voltage waveforms, just you follow this procedure. Why you are having the line voltages means, here we have the three phases na, like phase A, phase B, phase C. If you go through this three phase full wave converter, at any time 2 SCRs will be in the on state. If 2 SCRs will be in the on state, the voltage between the two phases is transmitted to the load. The voltage between the two phases is simply called the line voltages. So here we have the three phases, then 6 line voltages are possible, like VAB, VAC, VBC, VBA, VCA, VCB. 6 line voltages are possible. Hence why we concentrate on line voltages. If we go through the three phase half wave converter, at a time single SCR will be in the on state. So the phase voltage is transmitted to the load. So we concentrate on phase voltages, no problem. But if you go through the three phase full wave converters, the line voltages must be available across the load. So we concentrate on line voltages. So how you draw the line voltages? You clearly indicates which is VAB, which is VAC, VBC, VBA, VCA and VCB. Hence why to draw those line voltages, you follow the simple procedure here. Just take one small vertical line and horizontal reference line, which is taken as omega t. Below the reference line and above the reference line, you draw two horizontal dotted lines. And vertically, first you consider, for example, this is the 30 degrees, this width, then another 30, 30, 30, 30, like that you take one cycle. After that, you divided these first 4 boxes as the square and you put the cross mark. And next to 4 boxes, put the cross mark. Next to 4 boxes, put the cross mark. Similarly here also. These 4 boxes considered as the square and you just can draw the cross. This one. After that, you join the alternative peaks. That means from this you ignore this one and this one. Alternative peaks like this. And from this you ignore this one and next one like this. And after that this one, this one. And similarly here it is. Alternative peaks you just join. This one. Bottom side also alternative peaks. Like this. And from this you take the reference. Here it is the reference. You take 0 from this onwards. You ignore that first 30 degrees part. And here onwards you take the reference 0. After that 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360, 390, 420. And here this 0 to 60, this is the representation of VCB line, and 60 to 120, this is the representation of VAB line, and 120 to 180 VAC, 180 to 240 VBC, and here VBA, and here VCA, and this one VCB. This is the line voltage representation. So 0 to 60 VCB is the more positive. other than the line voltages. Similarly, 60 to 120, VAB is more positive. 120 to 180, VAC is more positive. VBC, VBA, VCA, VCB, like that. So, if you understand these line voltages, then it is easy to draw the output voltage waveforms and easy to derive the average DC output voltage for this three-phase full wave converter. Right. So, coming to the circuit diagram, first we go through the three-phase full wave converter with R load. The circuit diagram consisting 6 ideal SCRs which are numbered as T1 to T6. Here T1, T2, T3, T4, T5 and T6, the numbers are assigned to the respective SCRs depends upon the sequence of triggering of the SCRs. Depends on the sequence of triggering of the SCRs. That means if T1 is on, next T2 is on, T3, T4, T5, T6, again T1, T2, T3. In that manner, we are able to provide the firing pulses to the respective SCRs. Hence, those are numbers from T1 to T6. Right. Out of these 6, here T1, T3, T5 are called upper group SCRs or positive group SCRs or odd number SCRs. The odd number SCRs T1, T3, T5 are simply considered as the positive group SCRs or upper group SCRs. And the even numbered SCRs T2, T4, T6 are considered as the lower group SCRs or negative group SCRs. So, these are simply considered as the positive group SCRs and these are simply considered as the negative group SCRs. So, what is that positive group and negative group means? Here the phase A is connected to the T1 and the T4. Phase B is connected to the T3 and the T6. Phase C is connected to the T5 and the T2. So, if you go through the positive group, if phase A is more positive or if A is positive half cycle, phase A is positive half cycle, then T1 is in forward bias. If phase A is in negative half cycle, T4 comes to the forward bias. Similarly, phase B, if it is positive, T3 forward bias. Phase B is negative, T6 is in forward bias. Similarly, if phase C is more positive, T5 is forward bias. Phase C is negative, T2 is in forward bias. That is the representation of positive group SCRs and the negative group SCRs. Here, on phase A we keep T1, T4. On phase B, T3, T6. On phase C, T5 and T2. For sake of simplicity, for easily understand that explanation of operation, we will assign the numbers like T1, T3, T5, T2, T4, T6 like. So, coming to the here, the phase difference between two consecutive positive group SCRs is 120 degrees. That means if T1 is on at 0, next 120 degrees T3 comes to the on state. After 120 degrees T5 comes to the on state. So, the phase difference between two consecutive positive group SCRs is 120 degrees. After T5, again T1. 3, 5, 1. 1, 3, 5, 1, 3, 5. That is the sequence of the positive group SCRs. Coming to the negative group SCRs, 2, 4, 6, 2, 4, 6. So, the phase difference between two consecutive negative group SCRs is, two consecutive negative group means between T2 and T4 is 120 degrees. Between 4 and 6, 120 degrees. Again 6 and 2, 120 degrees. Like this. The phase difference between two consecutive positive group SCRs is 120 degrees. The phase difference between two consecutive negative group SCRs. Negative group means 2, 4, 6. Even number SCRs. After 6, again 2, 4, 6. That is the cycle. So, positive group means 1, 3, 5. Again 1, 3, 5. Like that. Negative group means 2, 4, 6, 2, 4, 6. Here the phase difference between these two and these two and these two 120 degrees. Between 2 and 4, 4 and 6, 6 and 2 120 degrees. And the phase difference between positive group SCR to the negative group SCRs is 60 degrees. The phase difference between positive group SCRs to the negative group SCRs is 60 degrees. That means if T1 is on at 0, T2 is on at 60. Again T3 on at plus 60, 120. Here it is 0, it is 120. We will go either this combination or this combination. 3 points. The phase difference between two consecutive positive group SCRs is 120 degrees. The phase difference between two consecutive negative group SCRs is 120 degrees. And the phase difference between positive group SCR to the negative group SCRs is 60 degrees. Consecutive positive negative, like between 1 and 2, phase difference is 60. Between 2 and 3, 60. 3 and 4, 60. 4 and 5, 60. That is the mean. If you understand this point, then easily draw the output voltage wave. Right. And observe here VCB is the output voltage. Here these are the line voltages, and for alpha equal to 0 degrees, this is the output voltage representation. That means for alpha equal to 0 degrees, VCB is available across the load from 0 to 60. 60 to 120 VAB is available across the load. 120 to 180 VAC is available across the load, and corresponding that. So what is the meaning of this VCB VAB means? If we go through that, alpha equal to 0, 0 to 60, what is V naught? VCB. So VCB means the left subscript represents positive group SCR and second subscript represents negative group SCR. Here total we have phase A, phase B, phase C. See, phase A, phase B, phase C. Here 1, 3, 5 connects to the positive group, 4, 6, 2 connects to the negative group. VCB na, here it is the positive group SCRs and this is the negative group SCRs. VCB, C means positive group SCR. Phase C positive group SCR is 5. Phase B negative group SCR is 6. That means here T5, T6 are on state. From 60 to 120, what is the output voltage representation here? VAB. VAB means phase A positive group SCR 1, phase B negative group SCR 6. So T1, T6 will be in the on state. And 120 to 180, what is V naught? VAC. VAC means phase A positive group SCR T1, phase C negative group SCR T2. Next 180 to 240, what is V naught? 180 to 240 VBC. See here 180 to 240 VBC. VBC means T3, T2. 240 to 300, what you are getting? VBA. What is VBA? T3, A, T4. 300 to 360, V naught. 300 to 360, VCA. CA means T5, T4. And 360 to 420, again V naught is equals to VCB, again T5, T6, that is the continuation. Again it will be repeats, VCB. So if you go through the alpha equal to 0 degrees, T1 is on at 60 degrees. You can observe here, this one. If you go with the alpha equal to 0, then T1 on at omega T is equals to 60 degrees onwards. If T1 is on, if you know the T1 conduction period, then we will easily identify the remaining SER's conduction period. Yes, you understood? If you go with the alpha is equal to 0, this is the representation of output voltage waveform, and this is taken as the reference voltage. If you go with the alpha is equal to 0, here T1 comes to the on state at omega T is equal to 60. If you go with the 3-phase half wave converters now, if you choose alpha equal to 0, where the T1 comes to on state, plus 30 degrees. If you go with the 3-phase half wave converter, irrespective of the firing angle, you add 30 degrees. Why? Because from 30 to 150, T1 is in forward bias. If you go through the full wave converters, similarly, here you assume 60 degrees must be added to the firing angle. That means, if you choose alpha equal to 0 degrees, then T1 is on at omega T is equals to 60 degrees. So if you choose alpha equal to 0, then we draw the timing diagram. Depends on the timing diagram, we easily identify which SCR comes to the on state and how the output voltage will be available. Just draw the timing diagram here. So here I just want to draw the timing diagram for alpha equal to 0 degrees. For alpha equal to 0 degrees. So if you choose alpha equal to 0, where the T1 comes to on state? Plus 60. So T1 on at 60 degrees. So from 60 degrees to, and I said the conduction period of each SCR is 120 degrees. The conduction period of each SCR is 120 degrees. So from 60 to 180, T1 will be in the on state. After 180, T3, next positive group SCR, 180 to 300. Next T5. Before this T1, T5. Here this is the representation of positive group SCR's conduction periods. If you go through the negative groups, if T1 is on at 60, where the T2 comes to on state, I said the phase difference between positive group SCR to the negative group SCR is 60 degrees. So if T1 is on at 60, then T2 comes to the on state at 120 degrees plus 60. So from 120, and the conduction of each SCR is 120 degrees. So from 120 to 240, T2, and 240 to 360, T4, and T6, next to T2. So before T2, what do you have here? T6. This is the timing diagram. So from this timing diagram, you are also getting 0 to 60, T5, T6. If T5, T6 are in the on state, 5, 6 are in the on state, first subscript represents the positive group SCR, second subscript represents negative group SCR. 5, 6 na, 5, 6. Then output voltage is VCB, this one. So nothing but this one. Here I just explain how you draw this reference voltage. Okay. Next, for different firing angles, how you draw the output voltage waveform, we will see now. Right. Now, for alpha equal to 30 degrees, first we draw the timing diagram. So, if you choose alpha equal to 30 degrees, na, so if you choose alpha equal to 30, where the T1 comes to on state, you blindly add plus 60. Then T1 comes to on state at omega T is equals to 90 degrees. So go through that. 90 to 90 plus 120, 210. 90 to 210, T1, 210 to 330, T3, next T5. Before this, T5. If T1 is on at 90, where the T2 comes to on state, plus 60 degrees, that is from 150 onwards, from 150 to 270, and from 270 to 390, T4. This T2, T4, next T6. Before this, T6. It's very, very important. The end portion of the T6 is 150. We know the conduction of each S here is 120 degrees. So 150 minus 120, 30. That is from 30 to 150, T6, and before this, T4. Before this, T4. It's very, very important. Actually, I am taking alpha equal to 30. If you take alpha equal to 30, T1 is on at 90 degrees. So 90 to 210 T1, T3, T5, 0 to 90 T5, no problem. If T1 is on at 90, T2 comes to the on state after 60 degrees. So 150 to 270 T2, T4, T6 like that. Before this T2, T6, no problem. We know ending in the portion 150. Starting portion is 150 minus 120, 30. So 30 to 150 T6 and before the T4. From this, observe 0 to 30. Which are in the on state? You tell first positive group SCR. After that you tell me the negative group SCR. 0 to 30. T5, T4. T5, T4 are in the on state. For sake of simplicity, I am writing here. These are positive groups and these are the negative groups. 5, 4 na? 5 phase C, 4 phase A. So, V0 is equals to VCA. Next, 30 to 90. Just you go through the timing diagram. If you draw the timing diagram perfectly, then it is easy to draw the output voltage waveform. 30 to 90. What is the conducting SCR here? T5, T6. If 5, 6 are in the on state, what is the output voltage? T5, positive group, phase C. T6, negative group, B. So, V0 is equals to VCB. Next, tell me 90 to 150. 90 to 150, T1, T6. Then V0 is equals to 16 na? VAB. 150 to 210. 150 to 210, T1, T2. Then what is V0? 1, 2, VAC. 210 to 270. 210 to 270, T3, T2. 3, 2, VBC. 270 to 330, T3, T4. 34 VBA, 330 to 390, 330 to 390, T5 T4, which is the first one. So V naught is equals to VCA. So where we start, and again loop was continues. In this manner you are getting the output voltage expression. Coming to this, if you want to draw the output voltage waveform here, I just want to draw the output voltage waveform for alpha equals to 30 degrees. Then how it is? You go through this 0 to 30. So identify that one, 0 to 30. Here it is 30, 30 to 90, 90 to 150, 150 to 210, 210 to 270, 270 to 330, 330 to 390. Right. So 0 to 30. What is the output voltage? VCA. Then you blindly follows the VCA curve. 0 to 30. VCA. Where is the VCA? This one. This one. This is the VCA. So from 0 to 30, that is the output voltage waveform. 30 to 90. What is the output voltage? 30 to 90. VCB, then VCB curve. This is the VCB. This one is the VCB. Just you follow the VCB. 30 to 90. 90 to 150. VAB. Just you follow VAB. 90 to 150. 150 to 210 VAC, VBC, VBA, VC. So here it is VCA, it is VCB, VAB, VAC, VBC, VBA, and again VCA. Here this is the output voltage waveforms for alpha equal to 30 degrees. VCA means which SCRs will be in the on state? T5, T4. So if T5, T4 are in the on state, then here if T5, T4 are in the on state, then the current flow through the circuit is T5 resistive load, T4 phase A, and in this manner. So at any time two SCS will be in the on state, one from the positive group, another from the negative group. So this is the output voltage waveform for alpha equal to 30 degrees. Now we try to draw the output voltage expressions for output voltage waveform for alpha equal to 60 degrees. So if you want to draw the output voltage waveform for alpha equal to 60 degrees, then draw the timing diagram first. Timing diagram is very, very important. Timing diagram. It is 0, 30, 60, 90, 120, this one. So if you want to draw the timing diagram for alpha equal to 60 degrees, where the T1 comes to on state, if you choose alpha equal to 60, you add plus 60 degrees. Then where the T1 comes to on state, 120 degrees. Good. So from 120 to 240, T1 will be in the on state. From 240 to 360, T3 will be in the on state, and next T5. Before this 0 to 120, T5. If T1 is on at 120, where the T2 comes to the on state? Plus 60. If T1 on at 120, from this 180 to 300, T2 will be come to the on state. And 300 to 420, T4. Next, T6. Before this T2, T6. Ending portion is 180. What is the starting portion? 180 minus 120, 60. So 60 to 180, T6, and before this, T4. That is the simple representation of timing diagram. Once you finish the timing diagram, then you write the voltage table, like, see this, 0 to 60. Which one in the on state? T5, T4. 5, 4. First you tell positive group, next negative group. T5, T4. If T5, T4 are in the on state, what is the V0? Again you draw the simple one. So 5, 4. 5 phase C, 4 A. Then V0 is equals to VCA. 60 to 120. 60 to 120, 5, 6. I don't know which SCR comes to the on state. Simply depends upon the timing diagram. We draw the voltage table and after that we draw the output voltage waveform. Very, very simple. 5, 6. V0 is equals to VCB. From 120 to 180. 120 to 180. T1, T6. Then 1, 6. V0 is equals to VAB. 180 to 240. T1, T2. V0 equals to VAC. 240 to 300. T3, T2. VBC. 300 to 360. T3, T4, V0 is equals to VBA. 360 to 420, T5, T4, again V0 equals to VCA. Cycle will be repeated. So from this, you draw the output voltage waveform, 0 to 60, VCA. Go through that. Here, I just want to draw the output voltage waveform for alpha equal to 60 degrees. 0 to 60, na, you mark that one. This is 60, 120, 180, 240, 300, 360. So from 0 to 60, VCA is the output voltage. Then you follow the VCA curve. Where is the VCA curve? Here it is. 0 to 60, this one, this portion, 0 to 60. 60 to 120 is VCB, then you go through the VCB curve, this is the VCB curve na. So 60 to 120, this one, 60 to 120, that portion. 120 to 180, VAB, you follow the VAB curve. Next VAC curve, VBC curve, VBA curve, like that. So this is VCA, VCB, VAB, VAC, VBC, VBA, and again VC. So observe here, for alpha equal to 60, this is the output voltage waveform. How many pulses are generated here for completion of one full cycle? This is 360 degrees, one full cycle. How many pulses are generated? 1, 2, 3, 4, 5, 6. 6 pulses are generated in the output voltage waveform. Hence why this 3-phase full wave converter is also called as 6-pulse converter. This 3-phase full wave converter is also called as the 6-pulse converter. and here also for alpha equal to 30 degrees also. Here VCA is half and here VCA is half. Here it is 360. So let me count 1, 2, 3, 4, 5. Here it is half, here it is half VCA. Total 6. 6 pulses will be collected in the output voltage wave. And one more thing, last one, we draw the output voltage waveform for alpha equals to 90 degrees. For alpha equal to 90 degrees. Then just draw the timing diagram here also. So if you take alpha equal to 90, where the T1 comes to on state? 150 degrees. Just add plus 60. So T1 comes to the on state at 150. Each SCR conducts for 120. So 150 to 270 T1, 270 to 390 T3, next T5. Before this T1, T5. T5's ending portion is 150. What is the starting portion? 150 minus 120, 30. So 30 to 150 and 0 to 30 before T5, T3. If T1 on at 150, where the T2 comes to on state? 210. So 210 to 330. T2, T4, here it is T6. Ending portion is 240. Then what is the starting portion? 240 minus 120 and 0 to 120. T4. This is the timing diagram. Very simple. First, if you draw the timing diagrams, then it is easy to develop the voltages. Tell me now, 0 to 30. What is V0? Sorry. 0 to 30 which are in the on state? T3, T4. Then what is the output voltage? T3, T4 na? 3, 4 VBA. 32 sorry. See here, T6 ending portion is 210, 210 minus 120, 90 it is. 90 to that one and here it is T4. Right. So 0 to 30, T3, T4, okay. 30 to 90, T5, T4. 5-4, V0 is equals to 5-4, VCA. 90 to 150, T5, T6. V0 equals to VCB. 5-6. 150 to 210. 150 to 210, T1, T6, VAB. 210 to 270, 210 to 270, T1, T2. V0 is equals to VAC. 270 to 330, T3, T2. VBC. 330 to 390, T3, T4. T3, T4 na? 3-4, VBA. 390 to 450. What you are getting? 390 to 450, T5, T4. Same, V0 is equals to VCA, and that is a cycle repeated. Right. T3, T4 up to this one is sufficient. Right. Now we go through the output voltage waveform. 0 to 30. What is the output voltage? Actually VBA. Just we go through the VBA waveform. 0 to 30 VBA. Here I just want to draw the output voltage for alpha equals to V0. For alpha equals to 90 degrees. Right. So 0 to 30, what you are getting output voltage? 0 to 30 VBA, 30 to 90 VCA. First we go through the VBA curve. VBA, where is the VBA? This one. VBA, see, 0 to 30 we have the negative portion. So what is that negative portion? If the negative voltage is available, we have only resistive load na. Negative source means there is no output voltage. Hence why 0 to 30, 90, 150, 210, 270, 330, 390. So 0 to 30 VBA is the negative voltage, hence why there is no output voltage. Next 30 to 90, what is the output voltage? VCA. What is VCA here? See, yes. From 30 to 90 you go through the VCA curve, this one, VCA. 30 to 60 it is positive, no problem. 60 to 90 again negative, hence why we have output voltage only from 30 to 60. After 60 what happens? The negative voltage will be available across the SCRs, hence why they may goes to the reverse biasing. And after that 90 to 150 VCB, see, 90 to 150, this is VCB curve. 90 to 120 no problem, 90 to 120 we have positive pulse. After 120 to 150 negative pulse, so 0. Next 150 to 180 VAB, 0, 0, 0, like this. So it is VAB, VCB, VCA, VAC, VBC, VBA. This is the output voltage waveform for alpha equal to 90 degrees. So from these waveforms, what you observe here I am going with the only resistive load, 3-phase full wave converter with resistive load. These are the 3 different output voltage waveforms for alpha equal to 30 degrees, for alpha equal to 60 degrees and alpha equal to 90 degrees. From these 3 waveforms you conclude that if alpha is less than 60 degrees, then we are getting the continuous conduction mode, and alpha greater than or equal to 60 degrees, then we are getting the discontinuous conduction mode. Why it is called discontinuous? It will reach the 0, output voltage 0 here, corresponding that output current is also 0. Why? Because we are resistive load na, purely current is in phase with the voltage, hence why here 60 to 90 output current is 0, here output current is 0, output current is 0. So discontinuous conduction mode will be taken place. If you go through the 3-phase full wave converter with R load, if we maintain alpha less than 60 degrees, we are able to collect the continuous conduction mode, and alpha greater than or equal to 60 degrees, we are able to collect the discontinuous conduction mode. That is the representation of 3-phase full wave converter with R load, and these are the different output voltage waveforms. Very, very simple. For any firing angle, first you draw the timing diagram, Depends upon this timing diagram, you build this voltage table. After that, you draw the output voltage waveforms. Here, these are the three different output voltage waveforms of three-phase full wave converter with R load. So, in the next class, we will derive the average DC output voltage of this three-phase full wave converter with R load. Later, we go with RL load. Okay, thank you.